What if I told you that the future of medicine, computing, and even our understanding of reality itself might be hiding in some of the most unexpected places? We're talking about secrets buried in magnets we thought we understood decades ago, robots learning to help us in our homes just by watching, and ancient civilizations that built empires on something most of us try to avoid stepping in. Welcome to Science Report.
I'm Dr. Nova Sterling, and today we're diving into research that challenges our assumptions about the familiar and reveals complexity where we least expected it. From the quantum behavior of cobalt to machine learning systems that could revolutionize how we manufacture medical implants, the common thread here is that nature continues to surprise us when we look more closely.
And I'm Marcus Webb. What strikes me about today's lineup is how often breakthrough science comes from asking a simple question: what if we've been missing something? What if cobalt, a magnet that's been on periodic tables in classrooms for over a century, has been keeping quantum secrets that could transform computing? What if the key to assistive robots isn't programming every single movement, but letting them learn like we do, by watching?
Let's start with what I consider the most fundamental discovery in today's coverage, one that genuinely made me reconsider what we thought we knew about basic materials. Cobalt, element 27 on the periodic table, has been used in magnets, batteries, and alloys for decades. It's considered a textbook ferromagnet, straightforward and well understood. Except it isn't.
Now Nova, I have to admit, when I first saw a headline about cobalt having topological features, my eyes started to glaze over. Topological sounds like something from a graduate mathematics course. But you told me this could be genuinely significant for future technology. Break it down for me. What does topological actually mean in this context?
Think of it this way, Marcus. Topology in mathematics is about properties that don't change when you stretch or bend something. A coffee mug and a donut are topologically equivalent because they both have one hole. In physics, topological states refer to electronic configurations that are similarly robust, they don't easily break down or scatter when disturbed. This is incredibly valuable for information technology because it means data could be stored and transmitted with far less loss.
So we're talking about electrons behaving in ways that are inherently protected from interference? That sounds almost too good to be true for computing applications where quantum noise and thermal fluctuations are constant enemies.
Precisely. The research team, led by Dr. Jamie Sanchez-Barriga at the Helmholtz-Zentrum Berlin, used a technique called spin-resolved angle-resolved photoemission spectroscopy, or SPINARPS for short. What this allows you to do is measure not just the energy of electrons in a material, but also their spin orientation and momentum simultaneously. It's like being able to see a three-dimensional map of how electrons move and rotate inside a crystal.
And they did this at the Bessey II synchrotron facility in Berlin, correct? These synchrotron light sources are essentially massive electron accelerators that produce incredibly bright beams of light for probing matter. The fact that you need such sophisticated equipment tells me this isn't easy science.
Not easy at all. What the team discovered is that cobalt's electronic structure contains what are called entangled energy bands. Imagine you have two highways for electrons that cross over each other. At those crossing points, interesting physics happens. In cobalt, these crossings occur along extended paths in specific crystallographic directions, and they persist even at room temperature. That last point is crucial.
Why is room temperature so important? I know that many quantum effects only show up at temperatures close to absolute zero, which makes them impractical for real-world applications.
Exactly. Many topological materials discovered in recent years require cryogenic cooling to exhibit their exotic properties. Liquid helium temperatures, sometimes even colder. But cobalt is showing these topological features at temperatures you and I experience every day. That transforms it from a laboratory curiosity into a potentially practical platform for technology. The paper suggests cobalt could serve as what they call a highly tunable topological platform for future spintronic devices.
Spintronics, that's using the spin of electrons rather than just their charge to process information, right? I've heard this described as the next evolution beyond traditional electronics. What makes spin-based computing potentially better than what we have now?
Current electronics only use one property of electrons, their negative charge. We push charge around circuits, and that's how computers process ones and zeros. But electrons also have spin, a quantum mechanical property that can be thought of as a tiny magnetic orientation, either up or down. Spintronics aims to use both charge and spin, potentially doubling the information density and reducing energy consumption because you're not just shuffling charge around, you're encoding information in a more fundamental property.
The paper mentions that cobalt could be important for magnetic topological states specifically. How does the magnetic nature of cobalt factor into all this?
This is where it gets particularly interesting. Cobalt is ferromagnetic, meaning its atomic magnetic moments naturally align in the same direction. Most previously discovered topological materials are non-magnetic, and introducing magnetism often disrupts the topological features. But cobalt shows that you can have both ferromagnetism and topology coexisting. The entangled band crossings they observed are intimately connected to cobalt's magnetic ordering. This opens possibilities for controlling topological states with magnetic fields, which would give engineers another knob to turn when designing devices.
I want to make sure our viewers understand the significance here. We're not talking about discovering a new element or synthesizing some exotic material that exists only in a few laboratories. Cobalt is abundant. It's already manufactured at industrial scale. If these topological properties can be harnessed, the infrastructure to deploy cobalt-based spintronic devices already exists.
That's a valid point about practicality. However, I want to add appropriate caveats. This is fundamental research that identifies the properties exist. Translating this into working devices requires substantial engineering development. The researchers would be the first to acknowledge that demonstrating topological features in spectroscopy measurements is quite different from building a functional spintronic memory chip. But it does provide a roadmap that materials scientists and engineers can now follow.
Let's pivot to our next story, which also involves machines learning to do things more intelligently, but in a very different domain. Researchers at Universidad Carlos III de Madrid have developed a methodology for robots to learn arm movements by observing humans, combined with something called intercommunication between limbs. As someone who struggles to pat my head and rub my stomach at the same time, I'm intrigued by how robots handle bilateral coordination.
The challenge the UC3M team addressed is substantial. When humans set a table, we don't consciously calculate every joint angle and motor command. We observe others doing it, we internalize patterns, and our two arms coordinate naturally through neural pathways that have evolved over millions of years. Programming a robot to do the same task traditionally requires explicit coding of every movement, which is time-consuming, rigid, and doesn't adapt well to variations.
So if I want a robot to put a plate on a table, traditionally I'd have to specify, move arm to position X, rotate wrist by Y degrees, open gripper, lower by Z centimeters, release plate, retract. And if the plate is in a slightly different starting position, or the table is at a different height, the whole program might fail.
Exactly. The approach from UC3M combines observational learning, where the robot watches human demonstrations, with a communication protocol between its two arms. The key insight is that for tasks like setting a table, the arms aren't independent. When one arm is carrying a plate, the other might need to adjust its trajectory to avoid collision, or to stabilize objects already placed. By having the arms share information about their states and intentions, the robot can coordinate more naturally.
The researchers mention this is aimed at assistive tasks in domestic environments, setting and clearing tables, ironing, tidying up kitchens. For anyone with mobility limitations or elderly individuals who struggle with these daily activities, this could be genuinely life-changing technology. What's the current state of assistive robots in homes?
We've seen significant progress in recent years, but most deployed robots are specialized for single tasks. Robotic vacuum cleaners are common. Robotic lawn mowers exist. But general-purpose manipulators that can handle the variety of objects and situations in a real kitchen remain challenging. A kitchen might contain hundreds of different objects, from delicate wine glasses to heavy cast iron pans, each requiring different grip strategies, forces, and movement speeds.
And that's where the observational learning component becomes crucial, right? Instead of programming responses for every possible object and situation, the robot learns underlying principles by watching humans who naturally handle all these variations.
The methodology appears to extract what we might call motion primitives from human demonstrations. These are fundamental movement patterns that can be combined and adapted. When a human reaches for an object, there's a common pattern regardless of whether it's a cup or a plate. The robot learns these patterns and then modulates them based on the specific task context. The intercommunication between limbs adds another layer, ensuring that both arms work together rather than as independent agents.
I noticed the source article mentions this represents a step toward more naturally teachable service robots. The word teachable jumps out at me. The vision seems to be that eventually, you wouldn't need an engineer to program the robot. You could just show it what you want, and it would learn.
That's the long-term vision for learning from demonstration research. In principle, a caregiver or family member could teach the robot household tasks specific to that home's layout and the individual's preferences. Current systems typically require many demonstrations and controlled conditions, but the field is progressing toward more sample-efficient learning that requires fewer examples.
Let's turn to another story where machine learning intersects with material science. Researchers have developed an AI-assisted approach to optimize microelectrodischarge machining of next-generation biocompatible titanium alloys. That's a mouthful. Nova, help me unpack what all those terms actually mean.
Let's take it piece by piece. Microelectrodischarge machining, or EDM, is a manufacturing technique that removes material using electrical sparks. Imagine tiny lightning bolts precisely eroding a workpiece to create features measured in micrometers, that's millionths of a meter. It's useful for creating intricate shapes in hard materials that would be difficult to cut with conventional tools.
And biocompatible titanium alloys, those are metals designed to go inside the human body without causing adverse reactions? We're talking about things like hip replacements, dental implants, bone screws?
Precisely. Titanium and its alloys are prized for medical implants because the body generally tolerates them well. They don't corrode easily in bodily fluids, they're strong yet relatively lightweight, and bone can actually grow onto titanium surfaces and bond with them, a process called osseointegration. The specific alloy mentioned is described as next generation, suggesting improvements in properties like strength, flexibility, or manufacturing characteristics over current standards.
So the challenge is that you have these advanced titanium alloys designed for medical use, but machining them precisely is difficult? Why would better titanium be harder to work with?
Often, the properties that make a material excellent for its application also make it challenging to manufacture. Very hard materials resist wear, which is good for a hip implant that needs to last decades, but also resist being cut or shaped. Alloys optimized for biocompatibility might have different thermal or electrical properties than traditional machining expects. Micro-EDM is attractive because the electrical discharge can remove material regardless of hardness, but optimizing the process parameters requires balancing many variables.
And that's where the machine learning comes in. What parameters would you need to optimize in micro-EDM?
Discharge energy, pulse duration, pulse frequency, electrode material and geometry, dielectric fluid properties, gap distance between electrode and workpiece, and many others. Each of these affects the material removal rate, surface finish, dimensional accuracy, and whether undesirable effects like microcracks or thermal damage occur. Traditionally, engineers would run many experiments to find optimal combinations, which is time-consuming and expensive, especially with advanced materials.
The AI approach essentially learns from experimental data to predict which parameter combinations will give the best results, reducing the trial and error?
That's the general principle. Machine learning models can identify patterns in complex, multidimensional data that humans might miss. Once trained, they can suggest parameter settings for new situations without requiring full experimental campaigns. For manufacturing, this could mean faster development of processes for new materials, less wasted material from failed experiments, and more consistent quality in production.
The aerospace application mentioned alongside medical makes sense. Aircraft and spacecraft components also need to be strong, lightweight, and precisely manufactured. Are there other industries where this kind of AI-assisted precision machining could have impact?
Semiconductor manufacturing, micro-optics, precision instruments, microfluidic devices for laboratory on-a-chip applications. Anywhere you need to create tiny, accurate features in difficult materials, advances in micromachining have ripple effects. The specific contribution here appears to be demonstrating that machine learning approaches transfer successfully to next-generation biomedical alloys, which validates the broader applicability of these techniques.
Let me shift gears dramatically now, from cutting-edge robotics and materials science to something that might seem almost comedic at first but actually represents fascinating research into how civilizations rise and fall. According to new research covered by Ars Technica, the ancient Chincha kingdom in Peru may have built their power on seabird excrement. Yes, you heard that right. Poop.
This is actually a beautiful example of how environmental conditions shape human history, and how scientific analysis can reveal connections that historical records alone might miss. Guano, which is the accumulated excrement of seabirds and bats, is extraordinarily rich in nitrogen and phosphorus, the key nutrients that limit agricultural productivity in many environments.
For our viewers who might not know, the Chincha were a pre-Columbian civilization on the southern coast of Peru that flourished before the Inca Empire expanded to absorb them. What made them particularly notable?
The Chincha kingdom, which reached its peak in the centuries before Spanish contact, developed sophisticated maritime trade networks and was one of the few Andean societies to achieve significant economic influence outside the Inca system. When the Inca eventually incorporated them, the Chincha leader was reportedly given special honors, being carried alongside the Inca emperor himself during ceremonies. This suggests they held unusual prestige.
And the new research suggests that their economic power derived substantially from agriculture boosted by guano fertilization?
The hypothesis connects several established facts. The coastal deserts of Peru are hyperarid, receiving essentially no rainfall. Agriculture requires irrigation, and even with water, the nutrient-poor soils limit productivity. However, islands off the Peruvian coast host massive seabird colonies. Anchovies thrive in the cold, nutrient-rich Humboldt Current, seabirds eat the anchovies, and over millennia their droppings accumulated into deposits sometimes hundreds of feet thick.
I've read that guano was so valuable in the 19th century that nations went to war over guano islands, and it fueled the industrial agriculture revolution before synthetic fertilizers were developed. So the Chincha may have tapped into this resource over 1,000 years earlier?
That appears to be the argument. By accessing and distributing guano as fertilizer, particularly for maize production, the Chincha could generate agricultural surpluses that drove their economy and political power. Maize was not just food but also the raw material for chicha, a fermented beverage central to Andean social and ceremonial life. Controlling maize surplus meant controlling key social resources.
What kind of evidence supports this interpretation? We're talking about events from centuries ago in a society without written records in the European sense.
Researchers use multiple lines of evidence. Isotopic analysis of ancient plant remains and human bones can reveal what fertilizers were used and what people ate. Nitrogen isotopes in particular differ between guano-fertilized and unfertilized crops. Archaeological excavation reveals storage facilities, trade goods, and agricultural infrastructure. Comparison of Chincha agricultural capacity with other regional societies shows they achieved unusual productivity for their environmental constraints.
It's a reminder that human civilizations don't exist in a vacuum. Environmental conditions, access to resources, even the behavior of seabirds eating fish can shape which societies rise to prominence and which don't. There's an almost elegant causality: ocean currents bring nutrients, fish thrive, birds congregate, excrement accumulates, humans discover its value, and empires emerge.
It also illustrates the importance of what archaeologists call control over production factors. The Chincha may have had political or logistical control over guano extraction and distribution, creating economic dependency from other groups who needed the fertilizer. This is analogous to how control over oil, or rare earth elements, or semiconductor manufacturing shapes modern geopolitics.
Let's round out our coverage with two stories about technology that viewers might have already experienced indirectly. First, the new drone-mounted cameras providing immersive coverage of Winter Olympics events. Second, the broader implications for how we experience sports and events through technology.
The technical challenges of capturing first-person footage of athletes competing at high speeds in mountainous terrain are substantial. A drone following a downhill skier needs to maintain safe proximity while matching speeds that can exceed 100 km per hour, navigating unpredictable wind conditions, and producing stable, broadcast-quality video in real time.
I watched some of the coverage, and what struck me was the visceral sense of speed and danger that traditional fixed cameras can't convey. When the drone follows a luge athlete through a banked turn, you genuinely feel the acceleration. It transforms viewers from distant observers into something closer to participants.
The engineering involves several sophisticated systems working together. Autonomous tracking systems that keep the athlete centered in frame. Stabilization gimbals that smooth out the drone's movements. Obstacle detection and avoidance to prevent collisions with terrain, trees, or safety equipment. Low-latency video transmission so broadcast directors can incorporate the footage in real time. And battery systems capable of operation in cold conditions that typically degrade lithium-ion performance.
The cold weather aspect is interesting. I imagine drones designed for temperate conditions might struggle in alpine or Nordic environments where temperatures drop well below freezing.
Absolutely. Battery capacity decreases significantly at low temperatures, reducing flight time. Lubricants in motors and bearings can thicken, affecting responsiveness. Camera optics can fog or ice over. The systems deployed for Olympic coverage represent engineering optimized for these specific conditions.
Beyond sports broadcasting, where do you see drone camera technology heading? This seems like a stepping stone to broader applications.
Search and rescue in remote terrain, wildlife documentary filming that previously required expensive helicopter operations, infrastructure inspection for bridges and power lines, real estate and construction documentation. As autonomous flight systems become more reliable and regulations evolve to accommodate them, the applications expand. What we're seeing in Olympic coverage is a high-profile demonstration of current capabilities.
As we wrap up today's coverage, I want to step back and look at the connections between these stories. We've gone from quantum physics and magnets to robots learning by observation, from precision manufacturing to ancient civilizations powered by bird droppings, to cameras that make us feel like we're skiing down a mountain. What ties these together?
Each story involves looking more carefully at systems we thought we understood and finding unexpected complexity or opportunity. Cobalt was supposed to be a simple ferromagnet, it turned out to harbor topological features. Robot motion was supposed to require explicit programming, observational learning offers another path. Optimizing machining processes was supposed to require exhaustive experimentation, machine learning accelerates it.
And the Chincha story reminds us that this pattern extends through history. The value of guano as fertilizer was always there, encoded in its chemistry. The Chincha apparently recognized it centuries before European scientists systematically studied plant nutrition. Discovery often means paying attention to what was present all along.
There's also a theme of integration across what seem like separate domains. The cobalt research connects solid-state physics with information technology. The robot research connects computer vision with biomechanics. The micromachining work connects materials science with artificial intelligence. The most interesting developments often happen at these boundaries.
For our viewers who want to follow up on these stories, I'd encourage looking into the source materials. The cobalt research comes from the Helmholtz Zentrum Berlin, and the measurements were done at the BESI 2 synchrotron. The robot work is from Universidad Carlos III de Madrid. The micromachining research involves biomedical engineering and materials science communities.
And for those interested in the intersection of technology and society, the guano story illustrates how environmental archaeology continues to reshape our understanding of pre-modern economies. The field has advanced dramatically with isotopic analysis and other scientific techniques applied to archaeological materials.
Before we sign off, Nova, if you had to pick one story from today that you think will have the biggest long-term impact, which would it be?
I'd choose the cobalt topological research, and I'll explain why with a caveat. Fundamental discoveries in materials physics often take decades to reach technological implementation, if they ever do. But when they succeed, the impact is transformative. Transistors emerged from basic research into semiconductor physics. Lasers emerged from quantum mechanics. Giant magnetoresistance, which enabled modern hard drives, emerged from thin-film magnetism research.
So you're making a long-term bet that understanding the topological properties of common magnetic materials could eventually lead to new computing paradigms?
That's the possibility. The advantage cobalt has is that it's already industrially available and shows these properties at room temperature. If spintronic devices can be built on this platform, the barriers to deployment are lower than for exotic materials. But I want to emphasize the conditional nature of this prediction. Many promising fundamental discoveries don't translate to technology, and the ones that do typically take longer than anyone expects.
For me, I'd pick the assistive robotics story, purely because of the human impact angle. The number of people who could benefit from capable home assistants is enormous and growing as populations age globally. If observational learning can make robots more teachable and adaptable, we're closer to genuinely helpful domestic robots rather than specialized single-function gadgets.
That's a fair perspective, and it reflects different values in assessing impact. Fundamental physics seeks to understand nature whether or not applications emerge. Applied robotics seeks to solve immediate human needs. Both are valid priorities.
That's all for today's science report. We've covered quantum surprises in familiar magnets, robots learning like humans, AI-optimized manufacturing for medical implants, ancient civilizations built on unexpected resources, and technology bringing us closer to athletic competition than ever before.
The common thread is that science continues to reveal complexity and opportunity where we least expect it. Whether examining materials we've used for decades or civilizations that flourished centuries ago, careful investigation uncovers new understanding.
Keep asking questions, stay curious, and we'll see you next time on Science Report.
Until then, remember that the most interesting discoveries often come from looking more carefully at what we thought we already knew.
I'm Marcus Webb.
And I'm Dr. Nova Sterling.
Thanks for joining us.
The science never stops, and neither should our curiosity about it.